Students love in-class demonstrations, and I love to do them, but I'm actually very selective. Demos not only have to be entertaining, they must also help students learn the day's lesson. This one, though only average as entertainment, is my favorite because it reinforces 4 major topics we are discussing in class: acid-base neutralization reactions, precipitation reactions, net ionic equations, and limiting reagents. As one independent variable is changing, the volume of added sulfuric acid, 3 dependent variables are changing, all in different ways. And the student who really understands electrolyte solutions can understand everything. I presented this demonstration at a major national conference just as I do in the classroom. Try your hand on all the votes. I'll bet you don't get them all right. I do this in general chemistry in the 5th week of the semester. Can everyone hear me? And students are familiar with the electrolyte light, which goes on when the solution is conducting electricity, which happens when there are ions in solution. And by the 5th week, I know the names of my students. I have about 60 or so. So I will be calling on you by name. It just won't be your name. So I'm going to first pour some barium hydroxide, aqueous barium hydroxide, into this fine tube. While they're doing that, we'll take our first vote. I'm going to put the electrolyte light in there. How many think the light will go on? Yeah. And how many think the light will not go on? Okay. Katie, I don't think you voted. What do you think?
Like a sign?
No, you have to take a position on this. I'm sorry. Aqueous barium hydroxide. It won't? Okay. We have a vote. We have taken a stand. So let's put it in there. Right. So why did the light go on? Jake. It's aqueous. So any aqueous solution, the light goes on? No. Anybody else have an idea? Matt. We have ions in solution. When we have aqueous barium hydroxide, that's making barium ions and 2 hydroxide ions for every 1 barium hydroxide. So that has ions in solution. And now I'm going to put a couple drops of phenolphthalein in there. And we haven't had this yet in class. Phenolphthalein is an acid-base indicator, which is pink in a solution that's basic, but it's colorless in a solution which is neutral or acidic. So I'm going to put the phenolphthalein in here, and how many think it will turn pink? And how many think it will not turn pink? Marie, what do you think? It will turn pink? Okay. Well, let's try it. Put the stirrer on here. So how does Marie know that that was going to turn pink? How do we know that this is a basic solution? It has hydroxide ions. Whenever we have hydroxide ion in solution, it's pink. And now from this diuretic, I'm going to add some sulfuric acid. Not a lot, just a little bit. How many think? I'm only adding a little bit. How many think the light will go out? And how many think the light will not go out? And how do you think the pink color will go away? I'm only adding a little How many think the pink color will not go away?
He said he's going to add it.
Ryan, do you go? Ryan. Okay. Let's try.
There's one more choice.
Yeah.
Go away slowly.
Go away slowly. Well, I'm going to add a little bit and turn off the stopcock, and then we're going to see what it settles down to. And is anything else going to happen? Will we see anything? An explosion, maybe? A precipitate? Jenna thinks we're going to get a precipitate. So why didn't the light go out? Still have ions. Why didn't the pink go away? And what else did we observe? What else do we observe? It kind of turned, well, it's obscured by the pink, but it turned a little white and opaque. And so Jenna was right. We do have a precipitate. Precipitates can sometimes be in the form of emulsions, suspensions. And that's what we have here. And how did Jenna know that we were going to get a precipitate? Well, we added aqueous sulfuric acid. And to understand this reaction, we have to write the ionic equations. And we've just done in class, the reason I like this so much is we've just introduced precipitation reactions, acid-base neutralization, and writing equations with molecular and ionic equations. So let's see if we can figure out how to do this. How does sulfuric acid dissociate in water? Two, of course, that H pluses.
Okay. And the sulfate.
And the sulfate stays together. Penny knew that sulfate stays together because she's learned for polyatomic ions. And that last hydrogen ion may not always come off. There's an equilibrium, but that's next semester. And so, now we can see how Marie knew that there would be a precipitate, because what precipitate will form from this? Barium sulfate is an insoluble salt, so it'll make a precipitate. And what else will happen? We've just seen that H pluses combined with OH minuses, and we have two H pluses and two OH minuses. Is that right? No, what's wrong with that? See, we do the balancing later. We know that the compound that forms is water. And to balance the equation, we put two in there, but we have to put the right compound there. So why did the light stay on? Well, the way I do stoichiometry is the way most people do equilibrium. Not too many people do stoichiometry this way. Oh, I've seen J10S, some people do. So I do like the ice diagram. So I'm going to put moles start, change, and for the actual numbers here, it's more convenient to use millimoles, which is 1,000th of a mole. So I put in about, in the barium hydroxide solution that I added, there were about 8 millimoles of barium hydroxide. And each barium hydroxide is one barium ion and 2 hydroxide ions. So I'll get 8 millimoles of barium ions from my 8 millimoles here. I got 16 millimoles of hydroxide ions. And I didn't add much sulfuric acid, only about 1 millimole. So from one of this, I get 2 of these and 1 of these. And before it reacts, there aren't any of these. And then it's going to react until the limiting reagent is exhausted. So the hydrogen ion and the sulfate ion will go to 0 at the end, which means I have to lose 2 hydrogen ions and 1 sulfate ion, so they're going to react completely. And the change line, the numbers there are always in proportion to the coefficients in the balanced equation. So it's 1 of these and 2 of these, 2 of these and 1 of these, make 1 of these and 2 of these. So I lose 1 millimole here, 2 millimoles here, 1 here, 2 here. So this is what I have now at the end. I have some barium sulfate, and it's a suspension, that's why it turned white. And the reason the light is still on is that I still have ions in solution. And the reason it's still basic is that I still have hydroxide in solution. And now I'm going to add more sulfuric acid, a bunch more. And how many think the light will eventually go out? And how many think it won't? And how many think the pink will eventually go away? And how many think it won't? Let's try it. And as you can see, the light stays on. And the pink remains. And nobody going that way. So I'm sorry to see that. Lights out. What happened to the pink color? So why did that happen? Why did the light go out?
No ions.
No ions left. Why did the pink color go away? No hydroxide. So now we have a different situation. We are at the equivalence point. We're at we've added a stoichiometric amount of sulfuric acid, just the right amount to react with the amount of barium hydroxide I have. Not too much, not too little, just right. So here I add about 8 moles of sulfuric acid, which has 16 moles of hydrogen ions and 8 moles of sulfate ions, and they all react.
Oops, I meant to say millimoles, not moles.
So all I have is water and solid barium sulfate in suspension. So the light's out because there are no ions. Phenolphthalein has turned colorless because there's no hydroxide. And now I'm going to add even more sulfuric acid. How many think the light will go back on? And how many think it won't? And how many think the phenolphthalein will turn pink again? And how many think it won't? And how many think the precipitate will redissolve? I've never had anyone vote for that. Okay. There's always a first. And let's see what happens. And we add more sulfuric acid, and the light does indeed come back on, but the phenolphthalein does not turn pink. And the light came on because we have these ions in excess now. And it did not turn pink because there's no hydroxide ions in there. And tonight, on your WebAssign homework,
We have a hard time with the projector here, but there are several interesting variations that one can explore on the homework to test student understanding. What if we substituted barium nitrate for barium hydroxide? How about substituting sodium sulfate for sulfuric acid?
No homework.